Good day, friends. Let's continue to solve problems on conservation of momentum and also conservation of energy, of course. And the problem goes like this. Two stationary wedges of equal mass m, 2 kilograms, have smooth transitions to the horizontal surface and are initially positioned as shown in the figure above. A block of mass 0.5 kilograms slides down from height of 75 centimeters from the left wedge to what maximum height will the block rise on the right wedge? Friction is neglected. So to imagine it, it would be something like this. Yeah, in the figure, it might not seem as a perfect circle, but in fact it is. Yeah, it had to be circular, if you can imagine it. And we definitely can see that the trajectory of this small block to go like this, and then go up here. Yeah, right? And let's imagine that it has some height, initial height, which is 75 centimeters, as it was said in the beginning. And we understand that after going here, it might go maybe, just maybe, it might not go so far. Maybe it will stop here. Maybe it will reach this place, or maybe it will go above, right? But definitely physically, we can already say that it is not possible that it would leave this second wedge because due to conservation of energy, the potential energy, which is just right here, cannot lift it up higher than this position, right? And that's why we know that it will not even reach this place. It will not reach the same height. Why? Because these two wedges are movable. They can move. And when this thing moves, we definitely know that it will act with some certain force and then push this block. Also, it will push this block. And when it wastes its potential energy, it does not waste it only to its kinetic energy, but also to some of the kinetic energy of these blocks. That's why we can definitely say that this block will rise probably maybe here. We don't know. We don't know yet. But we definitely know that this height, the last height that we are searching for, has to be less level than this, the initial one, because it loses some of its potential energy to kinetic energy of this one, kinetic energy of this one. Okay, logical. Physical part of the problem is analyzed. Okay, but let's try to solve this problem, right? To imagine it better, let me copy this image here, or first let me draw it and then copy it. When this block slides down at the very end of the first one, let's imagine that this is a very smooth transition. So this block will appear somewhere here, right? At the very beginning, it doesn't have any velocity. Yeah, it will slide down due to only its potential energy, and it will have some velocity 1, let's say, and this block will have its velocity 2, because every time when it slides down, of course, it pushes with some normal force. And this normal force has components like this one, and each of these horizontal components will just push this block to the left side. I hope that you can imagine it, but let's not complicate it. I just am trying to prove why this wedge on the left has to slide to the left. Yeah, it's pretty intuitive, but physical sense is like that. Every time we have normal force that is pushing it to the left, and it has some components, and only its horizontal component tries to push it to the left, right? Okay. Let's call this second. This is the second velocity, right? And let's say that it enters the second block with the same velocity, which is this one, because as I have told you, this is very smooth transition. So it would be something like this at this point when it leaves, and when it enters the second block, it's the same velocity. Okay, let me even draw it like this. Yeah, so when it leaves the first wedge and it enters the second wedge, it's the same velocity. Okay, agreed. And also, it will rise up to some height, I don't know, maybe here, as we have told you before. And of course, this thing would have its own velocity. Yeah, but it will not go upward anymore. Its velocity upward would be just 0 because it's the highest point. But it would still move to the right. Why? Because it still pushes this object. Both of them would go with velocity 3. And we need to understand this thing pretty good. Yeah. Okay. I think that we don't have to even copy it. I think that you can imagine it pretty much. We can divide this equation into two halves. Yeah. The first half, which is this one, then the second half, which is this one. Yeah. Let me write it as 1 and 2. Okay. Let's work with the first part. Okay. Let's write here conservation of momentum first. Yeah. We know the conservation of momentum, which is sum of all momentums in the beginning equals to sum of all momentums at the end. Okay, so we know that momentum has a formula of mv, and at the very beginning it does not have any momentum, right? That's why it would be just 0. At the end, it has some momentum. Yeah, this thing has its small mass. Yeah, this m, and it has velocity v1 going right. Yeah, then it's positive, definitely mv1. And also we have another momentum, which is this one. This wedge, this one, goes to the left, and we know that momentum is a vector. That's why it will be dependent on the direction. As it goes to the left, it must be minus. Yeah, right? This is minus mv2. Okay, if we move one of those to the other side, then we definitely can see that these, okay, this is mv1 equals to mv2. Okay, good. I hope that you understand. and it's pretty much logical. Okay, and what? Yet, let's not touch it, yeah, yet. And let's continue. Here I would continue conservation of energy. Energy in the beginning equals to energy in the end. Okay, this one is a little bit more tricky. This is interesting. At the very beginning, these wedges are not moving, this thing is not moving. The entire energy comes from potential energy of this block. So it would be just mg and h1. Yeah, let's call this height h1, and this height, which is which it will rise up in the second wedge, let's call it h2. Okay, good. It is mgh2, mgh1, and entire energy comes from it. So when it slides down, it does not have any potential energy left, yeah, because it is at its lowest potential. But instead, it has kinetic energy, and also the second wedge has kinetic energy. We can write it down like this. It is mv1 squared divided by 2, and also large mv2 squared divided by 2. I hope that you understand it. Okay, what can we do? As you can see here, it is m, small m, it is also small m, and I would suggest to change this large m to small m. How do we do it? From here, we can substitute or give some meaning to v2, right? v2 will hold the meaning mv1 divided by m, right? Okay, we can put it inside, and you would see something like this. This would be mgh1. This thing would be mv1 squared divided by 2, plus we still have here mass divided by 2, and also v squared is opened by this. Each of these elements will be squared, so it will be m squared v1 squared divided by m squared. Okay, good. And as you can see, we can cancel these out. Okay, we can continue it here. It would be mgh1. You can see that we can bring out the entire mv1 squared divided by 2 as a common factor. This thing would be left with 1. Yeah, we are taking it out, and we are taking this one of the m's, v1 squared, and 2 outside, right, as a common factor. Left with 1 plus one of the masses is still there, and also this large mass is still there. Yeah, so if we just take this thing and put it inside again, we would have the same result as this one. I think that you understand where it comes, right? If we continue this thing, it would be something like mv1 squared divided by 2, and also inside of the brackets we have what? If we give m to this one, then definitely it would be what? This thing has to be m plus m divided by m. Okay, good. And right now you can see this thing. I hope mgh1 equals, this is mv1 squared divided by 2, and here we have what? M plus m divided by large m. This thing would cancel out, m and m, and let's give some meaning to v1, maybe, just maybe. Let's move that 2 to another side, and v1 would have meaning, v1 squared, it would have meaning 2gh1, and this entire thing would just swap, yeah? Yeah, m goes up, and this thing goes down. Okay, it's the meaning of v1 squared. Okay, I think that for now it's enough. Let's highlight it. Maybe it would be useful later, but right now let's concentrate on the second part. Okay, second part, let's continue it maybe here, I believe. Okay, let's do it just below 1. Yep, the second part. It enters with v1. Yep, let's do again. Conservation of momentum and conservation of energy. I would copy it right here. We would do it once again, but with the second case. Yeah, the second part. For conservation of momentum, what can we do? We can see that it enters the second wedge with velocity 1, and it would be definitely mass v1 equals, and the second momentum would be what? Both of these things, this one and this entire wedge, they move together. Yeah, that's why it would be m plus m, and they move together with the velocity of 3. Okay, so that's why it would be what? M plus m. They act as one body, and this would be v3. Okay, good. For now, let's not touch it. Let's continue with conservation of energy. We can see that here it has some kinetic energy, and then it would waste its kinetic energy to go up, right? And it will waste its energy to potential energy, but also it wastes some of its energy to move itself and its this second wedge, yeah, with a velocity of v3. That's why it would look something like this. The initial energy, because at the very beginning the second wedge does not move. At the very beginning, only what we have is mv1 squared divided by 2. Yeah, it enters the second wedge with the same velocity as it leaves the first wedge. Yeah, okay, good. It does not have potential energy yet, and it will have potential energy at the end. It would be mg h2, I'm sorry, because it will rise up with height 2, right? And plus also they together move to the right. Okay, so it will be again m plus m. This small mass, and this entire large wedge, they act together and they have common velocity, which would be v3. So that's why it would be something like this: m plus m. This is v3 squared divided by 2. Yeah. Okay, we can move this thing. We can move this thing to another side. It would be minus. So let's write it like this: mv1 squared divided by 2 minus this m plus m v3 squared divided by 2. And it would be equal to mgh2. Okay, good. Right now we can substitute it. We can give meaning to v3. Yeah. And it would be what? It would be mv1 divided by m plus m. And we can put it inside of the v3, right? It would be mv1 squared divided by 2 minus this thing, m plus m divided by 2, but also v3 squared would be this, all of the elements squared. M multiplied m squared v1 squared. Is it v1? Yeah, v1. And below we have m plus m squared. Okay, one of the squares goes, this whole thing goes out, also equal to mgh2. Let's not forget about that. As before, we can take this thing, mv1 squared divided by 2, we can take it out. It would be 1 minus, yeah, we have taken one of the masses, yeah, not both of them, not squared, but just one of the masses. Squared velocity, we have taken it as well, yeah, as you can see, and also divided by 2. We just took this as well. So only thing that we're left with here is just one of the masses and this thing below, okay? Okay, so it would be inside, it would be m, this thing would be m plus m. And it will be equal to mgh2. And as you can see, we can cancel these masses out. Let's open the brackets. Not open the brackets, I'm sorry. Let's multiply this thing to this one. And then you would see that we'll have something like this: v2 squared divided by 2. Inside of brackets, it would be m plus m minus m. And below we have just m plus m, right? Equals gh2. Okay, as you can see, positive m and negative m just go out, and we would have inside only this m, a large m. Okay, and we can give some meaning to velocity 1. It would be what? It would be velocity 1 squared would be 2gh2, yeah, because these two just goes up. This mass goes down, and this thing goes up instead. Just basic proportion. I hope that you understand what am I doing, what I'm doing right now. M plus m, and below we will have just m itself, the large m. Okay, let's bring it closer. And as you can see, we have one more meaning of v1 squared. Let me highlight it. And as you can see, we have two meanings of v1 squared. This one and this one. Okay, let's make them equal to each other because they are. And let's do here. Let's bring it here. I would bring it here. I would bring this one here. I hope that you can see it, this one and this one. Both of them hold the same meaning of v1. That's why it means that this part equals to this part. They have the same meaning of v1 squared. And right now, as you can see, it's pretty convenient. 2g and 2g just cancel out. These two masses multiply to each other, and these two multiply to each other. And what we have at the very end, we were meant to find that height 2, it would be what? It would be, below we have m plus m squared, and above what we have is m squared h1, right? Okay, I think that it's too long. Maybe like this. Oops. Yeah, that would be good. Let's bring it closer. And let's try to put the values in and see if it's possible, if it is realistic. I would continue with red. Yeah, so you know that I'm just putting numbers in. This would be 2 squared. H is said to be what? 75 centimeters. It's just 0.75 in meters. M plus m. Okay, this would be 2 plus 0.5 squared. Okay, and this thing would be 4 multiplied 0.75. This thing would be 2.5 squared. Okay, above what we have is 3, right? And below what we have is 6.25. And if we divide those two, then it will give us 0.48, but it is meters because we have converted centimeters into meters. Our final result would be h2 would be equal to 48 centimeters. Okay, this is the last answer that we have, and it is correct. And it is possible, right? It's pretty much logical. If this block slides down from the height of 75 centimeters, it cannot go up higher because it cannot just gain energy somewhere. Yeah. It's also there is no friction. Yeah, we need to take into account. That's why it will not just stop somewhere. Okay. and it cannot go up the same height. It will not go to 75 as well, because it could go there without friction if these two wedges did not move at all. But right now, when it goes up, when it tries to go up to that 75 centimeters, it wastes some of its energy to move these wedge to the left and these wedge to the right. And then when it wastes some of its energy to kinetic energy of these two wedges, then of course it cannot keep its total potential energy, and it will go up only to some part of this entire height one. And that would be, logically, as we have said, this second height has to be lower than the first one, and it is lower than the first one. 48 centimeters, the first one is 75 centimeters, and it works. Okay, I hope that it was pretty much clear. If it was not, you can write me privately. Thanks for your attention. Goodbye.